Welcome to the third lecture. This is lecture 7, and we're going to do a quick, although not if you look at your watch, but relatively abridged overview of the electrical grid, so the grid 101 sort of. And I know for a fact this one's going to run a little bit long, hopefully no more than an hour or so. But after this, I think the lecture should shorten a little bit. So this is the figure that I showed the first day of class, and I wanted to give you a sort of bird's eye view of everything that's involved in the electric power sector, from generating electricity to transmitting it over high voltage transmission lines and distributing it, and the factors that go into the availability of different types of generation, like technology, regulations, and also the factors that drive electricity demand, like economic growth, changes in technology, weather and climate, and then also some of the outcomes that we pay attention to when we're thinking about whether the systems that we design are good. So the price of electricity, environmental impacts, and the reliability of power systems as well. So what we're going to do today is give a slightly more detailed overview of a bunch of these different areas. First things first, there's a difference between generation capacity and energy, and sometimes people can use these in a confusing, slightly interchangeable way. But capacity is, we measure in megawatts, and this is the theoretical ability to produce an amount of power per second, so what we could produce if we need it. Generation, or energy, or electricity, which is measured in megawatt hours or kilowatt hours or gigawatt hours, etc., is the actual production of electricity over an hour period. And so 1,000 kilowatt hours equals 1 megawatt hour, and 1,000 megawatt hours equals 1 gigawatt hour. So the overarching goal of any power system is to meet electricity demand. And an easy way to think about how this happens visually is if you picture changing electricity demand. And so on the y-axis here we have electricity demand, on the x-axis the hour, and this is for an entire week. 168 hours is 7 days. And you can see electricity demand going up and down each day, and this is summer electricity demand, so there's a big peak in the late afternoon when everybody's using their air conditioning, so electricity demand is highest then. And the goal is to fill in the area under this entire curve using different types of generation. So there's a lot involved in that, not just generation, but also the infrastructure that's needed to send electricity that's produced from the generator out to people's homes or to industrial customers, etc. And so we typically divide the grid physically into 3 different sections: generation, transmission, and distribution. And the main difference between transmission and distribution is that transmission is high voltage transmission. So we're transmitting electricity at very high voltages in order to reduce line losses, and we'll talk about why. And then that voltage is stepped down using transformers when you get close to load centers or concentrated areas where people are using electricity demand, and the voltage is lowered and then sent out over lower voltage distribution lines to individual customers. So this is on average where we get our electricity from in the United States. This graph is a couple years old. It shows the mix for 2014. So coal is at 39%. It's actually lower today. I'm not exactly sure what the exact number is, but it's lower than 39% and has been declining over the last several years. This shows nuclear at about 19%, natural gas at 27%. Nuclear is about the same, as staying about the same. Natural gas is increasing. That's what's mostly replacing coal. The other big thing that's increasing is wind and solar, although solar you see here doesn't quite make the cut, although I think as of 2016 solar is about 1% the generation mix. Hydropower you see here is 6 to 8% annually, depending on how much it rains and snows. And then oil is 1%. Oil is basically used just for backup generators. So this generation mix is not distributed evenly across the United States. Geographical resource limitations often determine what mix is used, as well as policy. So you can see that there are certain parts of the country where we produce a lot of coal, the Mountain West and Appalachia. These parts of the country are much more dependent on coal. You see these pie graphs in the Mountain West and Appalachia, mostly gray. In the Pacific Northwest, where we have a tremendous amount of installed hydropower capacity, those circles are almost blue, or a lot more blue, because there's just a lot more naturally availability of hydropower out there. California is an interesting case. You see no coal. That's an example of regulations, air quality regulations, prohibiting the use of coal in California, so they use a lot of natural gas. And in the southeast, you can see a lot of the states look relatively similar, with a dependence on nuclear, coal, and some natural gas. The other distinctive region is the Gulf Coast, where there's a lot of red, and this is because the Gulf Coast is near a lot of natural gas refinery activities, and so a lot of those states are heavily dependent on natural gas. This is basically the same figure, although significantly updated. This is using information as of June 2016. The colors are a little different here. You can see the color legend at the bottom. But the neat part about this is it actually shows you the physical location of different generating plants, and also the size of the generating plants corresponds to the size of the circle. And this is, I think, really nice. It gives you an idea of how wind is located in the Midwest, Texas, Oklahoma, Kansas, Iowa, etc. It shows you where the location of all the hydropower is in the Pacific Northwest. And North Carolina is really interesting, actually, too. You can see it's dotted with these small yellow circles, which are those 5-megawatt solar farms that have become really prevalent in North Carolina as a result of state-level policy, as well as federal rules, especially PURPA, that require Duke Energy to connect solar farms if developers build them. So let's go over the basic economic characteristics of thermal generators. So thermal generators would be nuclear, natural gas, coal, and oil, as well as hydropower. And we typically think about the economics of power plants in a couple different categories. We're not here talking about the cost of building them. These are the operational characteristics of power plants. So once you build them, how much does it actually cost to turn them on and off or generate different amounts of electricity? So the first thing we look at is the variable cost. So this is $1 per megawatt hour rate. And there are two different components of a plant's variable cost. The first are the fuel costs. So if you think about a plant needing a certain amount of coal or a certain amount of natural gas in order to create a certain amount of electricity, then fuel costs are basically proportional to how much electricity you produce, and that's why this is a variable cost. So the total fuel costs equal the fuel price, which is the $1 per million BTU price that you pay for natural gas or coal, times what we call the plant heat rate. And the heat rate for a thermal power plant is the ratio of the heat content of the fuel that has to go into the plant and basically be combusted in a boiler, the ratio of that heat content to how much electricity you can get out. And this is a direct function of what we would describe as the efficiency of the power plant. Now, the other part of variable costs are variable O&M. And so this just means that the more you use a plant, the more you produce from it, the more upkeep, regular sort of expected upkeep that you're going to have to pay to fix things that break, or grease turbines or whatever. Now the other is fixed costs. So that generally plants are associated with some sort of fixed hourly rate, some amount of money that it costs just to be online. And that could be paying employees, keeping the lights on, anything like that. The third category of operational costs are start costs. And so this is the dollar amount that the plant has to pay, more or less, if it is turned on from an idle state. And a lot of this has to do with how long it takes, how much fuel it takes to ramp the plant up so that it's generating at the correct frequency. So we have alternating current generators, and it takes a certain amount of fuel that you cannot sell that electricity from because it's not synchronized with the grid, but it takes some fuel and time to ramp up a plant to do this. And in the meantime, you have to burn a lot of money. So the general schematic for thermal power plants is shown here. This is the Rankine cycle for thermal power plants. And you can see the general process. If we start at number 1, we have some source of water. This is a closed loop system for this water, the blue water at number 1. That water is pumped, so it's compressed or pressurized in some way and sent to a boiler. And the boiler is where we're heating this water up until it turns into steam. And the source of this heat is whatever fuel we're using at the power plant. So that can be coal, it can be natural gas, it can be oil, it could be nuclear. And so the fuel input in, Q in, is the source of heat. It turns the water into steam, the pressurized fluid into steam, and the steam is passed through a turbine and depressurized. So the steam is allowed to expand in a greater area or a greater volume. And that expansion of the steam spins a turbine. And the turbine is attached to a magnet, and you have a magnet rotating in a coil, which produces an electrical current. And so when that steam is passed through the turbine, it's then recycled. You don't want to just exhaust that steam from the system because it's still pretty hot. And you want to cool it down so it turns back into liquid water, but you don't want to cool it down so that it's cold water. You want that hot water and the heat content of the water to be sort of recycled. And so you pass the steam through a heat exchanger. That's what this curved sort of teal coil is. So the heat exchanger, there's cold water coming into the heat exchanger, and that water is usually brought in from a river or a lake or a cooling pond or something like that. And it cools the steam down into water, and it absorbs some portion of that heat. And then that water is heated up and it's sent back out of the power plant, usually back into the river or lake. And then as that steam forms back into liquid water, it starts through the cycle again. It hits number 1, it goes through the pump and back through. So let's talk about some physical characteristics of thermal power plants and hydropower. So most plants have a minimum generating capacity depending on what type of plant it is. So power plants can't, if you have a 1,000 megawatt power plant, it typically is not going to be able to produce 1 megawatt or 2 megawatts even. There's some minimum amount of power production before the plant must be shut down, and this could be due to safety, design, or economic reasons. There's also a design or maximum nameplate generating capacity, and so this is a design limitation on the power plant. So all power plants have some sort of electricity production that they can't go beyond. A startup time, this is the time required to start plants and then synchronize their power production with the grid. And there are different types of power plants, and different ones have different startup times. For peaking plants, startup times could be minutes or hours. But for a base load power plant like nuclear or coal, the startup time could be several days. Other physical characteristics of power plants are minimum up and down time. And so this is a little bit of an abstract thought. So many power plants, once you turn them on, they have a minimum number of hours that the plant has to stay on. And same thing with if you turn a plant off, can be a minimum number of hours that the plant must remain off. And a lot of this can be tied to mechanical or design limitations, but in some cases it can be tied to economic decisions as well. Ramp rates define the maximum hourly change of generation. So if you're going from 1 hour to the next, a lot of plants have a limited ability to quickly change the level of power production. Some plants, peaking plants, have a great ability to change this rate of power production, and we use them in some cases specifically to do that. So all of these characteristics vary dramatically based on the design of plants, the fuel type, and the age. In general, plants that are characterized by really long or high start times and start costs, high minimum generating capacity, and high minimum up and down times, and low ramp rates, all of this would generally describe a plant with very low flexibility. We use these as baseload resources, so that we use them to provide steady electricity all the time. So we're talking about nuclear, coal, and in some cases combined cycle natural gas. Not really though. Plants with low start costs, low minimum up and down times, and high ramp rates are used as peaking resources. And we generally only use these to produce electricity during high demand periods. So the examples here would be hydropower, combined cycle natural gas, and combustion turbines that use either oil or gas. So think back to that graph I showed you of fluctuating electricity demand, and I told you that the goal, the objective here is to fill in all the area under that graph, or that curve, that electricity demand profile, with different types of generation, and of course the goal is to do that in a way that minimizes cost. That's how we sort of, and maximizes reliability. That's how we know we're doing this in the right way. And so because of the natural differences in flexibility and cost associated with all these different types of power plants, no matter what power system you're in the United States or even globally, we see a pretty similar pattern emerge about how different types of plants are used. Nuclear power plants provide base load electricity, and you see very little fluctuation on an hour-to-hour basis in the electricity output from nuclear power plants. Coal power plants are used in very similar ways, but depending on the system, they could be used to provide what we call base load and shoulder load, so almost peak load, but coal plants generally lack the flexibility to go all the way up these peaks and provide electricity. So to really, satisfy the electricity demand requirements during these true peak periods, we have to rely on gas or hydropower or even oil if need be. So I'm sure you're now at this point wondering about variable renewable energy and how it fits into this more traditional way we think about scheduling electricity and power systems. So wind and solar are not dispatchable, which means we have no control over when they're available. So we can't really consider them base load, because base load means we turn a plant on and we leave it on and we know it's going to be available for a long period of time. We also can't consider it peaking, because we can't turn it on or off at a moment's notice in order to meet changes in electricity demand. We think of wind and solar as must-take resources, and we view them as really a source of demand reduction. So if they're available, we use them. If they're not, we have to use something else. For solar power production, for a given solar farm or solar array, production is a product of the size of the panel, which we measure in area, the solar insolation, which you can measure in terms of energy per square meter or energy per area. And this is determined by the hour of the day of the year, the latitude, aspect, and tilt, etc. There's a lot of things that go into that. The efficiency, so the conversion efficiency of the solar cell itself to convert solar energy to electricity. This is generally between 15 and 22%, although the efficiency for all types of panels are sort of increasing. And then performance losses. There are a number of losses just inherent to operating solar panels at this point. Some of them can be temperature related. If solar panels are operating at really high temperatures because it's the summertime in North Carolina, you lose some electricity from heat loss there, as well as you can also lose electricity from inverters and other solar components as well. So the equation at the bottom gives you the output in kilowatt hours, so electricity, as a function of the area of the panel array, amount of solar insolation, efficiency, and performance losses. So first pass at what areas of the country are the best places to put solar panels can be done using a map. This shows the spatial differences in the availability of solar insolation as measured in kilowatt hours per meter squared per day. You can see that the south and the southwest are much better in terms of solar resource availability than, say, the Pacific Northwest or the Northeast. Now, this does not tell you by itself where the best place to own a solar panel is, because a lot of that decision comes on the economic side in terms of what your alternative is, in particular what the retail price of electricity is. So those two factors have to go into play here. So for wind power production depends on the amount of air, so the volume of air flowing through a given area, the speed of air, so wind velocity and the mass of the air. And so this is deriving the equation for wind power production as a function of kinetic energy and air mass. And so the equation at the bottom in red shows you this is wind power production as a function of the density of the air. That's the thing that looks like the P here. The area, and so the area here is the area of the circle created by the wind turbine rotors, and then V cubed. And so V here is the speed of the air. And so the first thing that should pop out at you here is what happens if you increase the area of the wind turbine, right? So power increases proportionally. So that's part of why we're seeing larger and larger wind turbines being built in the same area. The other thing you should notice is that wind speed is tremendously important in terms of determining wind power production. It's cubically related or wind power is cubically related to wind speed. So a relatively small increase in wind speed can result in a nonlinear or much bigger than linear increase in wind power production. So that equation defines the theoretical amount of energy that can be produced from a wind turbine, but really there's some, in practice, efficiency limit on the ability of a wind turbine to convert that flow of air into electricity. And this is called the Betz limit. The maximum possible efficiency that we see in wind turbines right now is 59%. And so if you want to account for this loss of this efficiency, so an imperfect ability to convert the kinetic energy of the wind into electrical energy, you just multiply. You can see the same wind power equation, P equals 1/2 times the density times the area times velocity squared, or wind speed squared, times the efficiency or the power coefficient here. And we can look at a map of wind resource availability that looks a lot like the map I showed you for solar. And so this has its own sort of distinctive geographical characteristics here. You can see that, number one, offshore wind is generally much higher than onshore land-based wind speeds. And so, that's part of why offshore wind has looked attractive just from an engineering standpoint. Now, it's much more costly, and that sort of offsets this advantage you have in greater wind speeds, but we are starting to see more interest in actual construction now in offshore wind, at least in the United States. And other countries have been doing offshore wind for a while. In terms of land-based wind, it's very clear that the middle part of the country is where all the good wind resources are. The problem there is that, of course, no one lives there. And so developing, the full extent of these wind resources in the Midwest would not only involve building wind turbines, but also a lot of transmission capacity to take all that wind power to urban areas and other types of load centers. So a commonly used term to describe the amount of electricity that's produced at a given power plant relative to how much electricity it could produce over a period of time is the capacity factor. And we generally express this as a percentage or a fraction over a long period of time, and it basically measures, it's a measure of usage, plant usage. So, for example, if you look at this figure, you see nuclear has the highest capacity factor. And that shouldn't be surprising because we know that nuclear power plants are used as baseload resources. So we turn them on, we ramp them basically up to 95%, and then we leave them on, almost the entire year. And you see some seasonal fluctuations here where nuclear capacity factors decrease in the spring when electricity demand is low, and every other part of the year they're pretty high. Geothermal here is pretty high. And this is part of why in some cases geothermal is an attractive resource, because you're constantly making use of this electricity and you're using geothermal as a baseload resource. Coal is pretty high, natural gas is pretty high, and then you get into wind and hydro, which hover between 20 and 40%. These are variable renewable energy resources, so you can only produce electricity when water's available, when wind is available. So you're not producing at plant capacity 100% of the time. Very lowest on this list are natural gas combustion turbines. So these are basically jet engines that use natural gas. They're very expensive to operate, and that's why they're never used. So these are basically backup generators that we only use in the most dire circumstances, like so really, really high peak summer electricity demand, we might use natural gas combustion turbines. Okay, so let's do a very brief simplified primer on transmission systems. We use alternating current generators and transmission systems in the United States. So electric power is transmitted as alternating current, and the main reason is because when the electric power industry was developed, the only way we knew how to increase the voltage of an electrical signal from a generator was by using alternating current. So we do that. We dramatically increase the voltage using a transformer, and this allows the power to be transmitted through lines efficiently at high voltage. This reduces the power lost as heat due to the resistance of the wire. So this equation, PL is equal to I squared times R, describes the power losses in a conductor. So the conductor here is the transmission line itself. So the power losses, which are mostly heat-related losses, resistive heat losses, are equal to the amount of current squared times the particular resistance of the conductor, which is a distinctive characteristic of different types of materials and the size of the conductor, etc. And so what this should tell you is that if the current here is doubled, if PL is equal to the power losses in a transmission line is equal to the current being transmitted squared times the resistance. If you double the current, the power loss is going to be 4 times as great. So in theory, if we want to minimize losses in transmission lines, what that I guess should tell you is that we should minimize the amount of current that we're sending, right? But there's a trade-off there because we want to send current. We want to send power over transmission lines to reach customers. Now, power that's delivered or transmitted is equal to the current times the voltage. And so if we know from the equation that describes power losses due to resistive heating or something on a transmission line, we know that we want to minimize the current to minimize those sorts of losses, but we want to keep the same power that's actually delivered to the customer, P equals IV, then what has to give here, right? So if we want to make I smaller here in this equation, but keep P equals the same, the one thing that has to change is V, right? And V has to increase if I goes down while P stays the same. And so what we've discovered is that if we transmit power at a really, really high voltage, that allows us to send the same amount of power over transmission lines at lower current levels. And that minimizes resistive losses in transmission lines. So that's why we have an AC power system, because when the electric power industry was first developed, we did not know how to increase the voltage of direct current power, and we did know how to do it using AC power, so that's what won out. So today we have AC systems. Many other parts of the world also have AC systems. You still see some legacy direct current systems in cities. But also high voltage DC transmission is sort of making a comeback, because in some ways it's easier to use when incorporating renewables. So here are the really simple basics of the mathematics of AC power. The main thing to remember here is that this is sort of a sinusoidal based system, right? So we have voltage that varies through time. And the equation for how voltage varies through time here is given V of t is equal to the V peak, which is the peak voltage, times the sine of the angular frequency. And this is given in radians per second. And you can convert the angular frequency here from radians per second to a physical frequency, which is how we typically think of the F. This is how we typically describe the frequency of the U.S. grid. And in the U.S., the entire grid has to be synchronized and be operating at the exact same frequency, 60 hertz. And then this is also a function of time, t. So I showed before the relationship between voltage and power is P equals IV. So if V is going up and down, right, because it's a sine wave, and I is going up and down, then of course power is going up and down. We can describe how power fluctuates as a function of peak voltage, the resistance of the load, and then this sine wave, right? This sine wave that's a function of whatever time it is, and the frequency that we're operating at. And then you can break down below the R and description of the resistance here. You can break down velocity again. It shows again how velocity changes as a function of time as well as current. So what this means is that it's more or less accurate to think that think of the electricity that we pull off of transmission and distribution systems as something that, the availability of power in that signal is something that changes through time. And it changes through time on a regular basis, right, at a very distinct frequency. Now that frequency is so high that we can't see this with the naked eye. We can't perceive this. And the only chance we would have is by sort of slowing, like video recording resistive heating, right? So incandescent lights or something like that, and taking pictures or a movie of that at really, really small time scales. But if we do that, we can actually see lights sort of not flickering on and off, but fluctuating a little bit. And that's what this picture is. They use some sort of special photography to look at, I think, street lights in some sort of city over a long period of time. And you can see this sort of pulsating, sort of dashed quality to a lot of these lines. And that's an indication of this regular variability in delivered power resulting from our use of an alternating current system. This gives you an idea of transmission infrastructure in the United States. This is color-coded by the size of the transmission line. So the the voltage of the transmission lines. And the highest voltage shown here is magenta. Those are 500 kilovolt lines. You can see some in Georgia, Alabama, Mississippi. The lowest are these gray lines or light blue lines, and those are 115 kilovolts. And those are sort of interspersed in most states, especially around to interface between higher transmission and distribution lines. Okay, so let's go through some really basic power flow issues. So there are a set of rules that determine how we can transmit power on AC lines in AC systems and circuits. The first is the Kirchhoff voltage law, and so what this is saying that the sum of voltage drops across any closed loop in a circuit must equal the applied voltages. So in the first diagram you have a 10 volt source, whether it's battery or generator or something like that. So it's creating 10 volts, and then you have these squiggly lines. These are resistances measured in ohms all the way around, and as the current goes across these sources of resistance, the voltage drops. And so the sum of all these voltage drops across the branches has to equal 0. So you're saying plus 10 and then minus 2, minus 2, minus 2, minus 2, minus 2, that equals 0. The other really important law is the Kirchhoff current law. And so what this is saying that the sum of all currents entering a node, and when we think about circuits and networks, we think about branches and nodes, so lines on which current can flow, and they flow into nodes and then out of node. And so the sum of all currents entering a node here must be equal to the sum of all the currents leaving the node. So if you have 5 milliamps, 10 milliamps, and 15 milliamps, then everything coming into this one dot, the node, has to be the same as everything leaving this node. And so this is another way of saying that power in power systems must be in balance at each node. So if we're talking about a node in a power system and it's UNC, whatever generation we produce here plus however much we import has to be balanced by however much we export and how much we consume. So we think of power systems in terms of networks. I mentioned this. So the nodes we call buses, and buses can be generators or aggregation of load or demand. And all of these buses or nodes are then connected by transmission lines, which from a math standpoint we call edges. And each of these transmission lines or edges is characterized by its impedance, which is kind of like resistance. So the impedance is a factor of resistance, but it also includes what we call reactance. So there's inductive reactance and capacitive reactance. Now, please don't ask me in class what those are. Ask a friend that is a physics major. I don't know how to explain it in an elegant way that will not make me sound like an idiot. So when we're thinking about power systems, though, or modeling power systems, we usually assume that the resistance of the line is actually negligible. So we generally assign the value of impedance equal to the reactance of the line. So when we're thinking about how power flows in a system, when there are different possible paths that it could take. So let's say we have current coming into this system, into node 1, and we have two lines, possible paths for that current to flow out of node 1 into node 2. So how do we know? I mean, if we know what's coming into node 1, and we know what's going to go into node 2, how do we know which branch things are going to take, right? How much of that current is going to go on branch A versus branch B? And so this slide basically gives you an idea of how mathematically that's determined. And I'm going to skip over this just a little bit. What we ultimately realize, which is just below this red just below the red text at the bottom, down here, is that what we discover is that we can describe the amount of current that flows on any one path, for example, on path A, as inversely proportional to the impedance of that path, right? So you have the flow of current on line A is equal to some fraction of the total current, I, and that fraction is equal to the impedance of line B over the total impedance, right? So of both lines, ZA and ZB. And so if the fraction of impedance, of total impedance, ZA plus ZB, in ZB increases, right? So that basically we can think about it as the resistance of line B. As the resistance of line B increases, the current flowing on line A increases, right? And so what this means is that current takes the path of least resistance. So if there's one line that has more resistance than another, then it will proportionally less current will flow along the path that has more resistance or higher impedance here. So we can make this as complicated as you want. And this is a pretty simplified example, but let's say we have 3 nodes, 1, 2, and 3, and then we have 3 generators, A, B, and C, and D, so 4 generators, A, B, C, and D, and 3 load centers, so 3 aggregated centers of electricity consumption, X, Y, and Z. We have 3 transmission lines, one connecting node 1 and 2, one connecting nodes 2 and 3, and one connecting nodes 1 and 3. Each of those transmission lines is characterized by a certain amount of impedance, which we're going to go ahead and say here is equal to reactance. And here we're just using the per unit values of reactance, so sort of standardized reactance. And then they each have a capacity limit. Each of the transmission lines has a capacity limit associated with it. And that's what the max is. So the maximum amount of electricity that can actually be sent. So let's say generator B at node 1 wants to sell 400 megawatts to load Y at node D. Is this transaction feasible? So what we have to figure out is, number 1, is there a way for a generator B to send 400 megawatts, and clearly it's not going to be able to just send 400 megawatts from 1 to 3, or 400 megawatts from 1 to 2. It's going to have to split that amount up. Is it feasible to split that amount of power up, 400, in a way that satisfies what we know about Kirchhoff's current law, right? So that flow has to be proportional to the or inversely proportional to the resistance of the line. And it also has to satisfy the maximum power capacity of each transmission line. So here we're using Kirchhoff's current law. We're describing the amount of flow on each path as capital F13 on line. That's path 1, going from 1 to 3. And then the capital F13 Roman numeral 2 is the path that power could take going from node 1 to 2 and then from node 2 to 3. And here we are saying that the amount of power that's flowing is inversely proportional to the resistance of those particular paths. And so the X's here are the reactance, right? That's what we're assuming, the per unit reactance or impedance of the lines. So will this work? We can actually solve for the amount of power flow on each line, and what we determine is that based on Kirchhoff's current laws, we should send 240 megawatts directly from node 1 to 3 and 160 megawatts from nodes 1 to 2 and then 2 to 3. So will this work? No, it won't work. And the reason it won't work is because we decided we wanted to send too much power across the lines 1 to 2 and 2 to 3. We wanted to send 160 megawatts from 1 to 2 and then 2 to 3, and we wanted to send 240 megawatts from 1 to 3. So the power flow that we determined using Kirchhoff's current law from 1 to 3 works. But the other side of this is constrained, right? So we want to send too much power than what our actual transmission lines can take. So the point of this is to illustrate the reality of transmission constraints. Even if we are connected, even if we're physically connected and the whole grid is connected except for Texas in the United States, there are other engineering physics limitations on our ability to send electricity from one part of a system to another. And a really interesting illustration of that is this map here. So it's a little hard to tell because of the colors, but this is the Midwest. So you can see at the bottom there's North Carolina, Tennessee, Kentucky, Missouri, Kansas, Nebraska. And when we get into the colors, it's Missouri, Indiana, Iowa, Illinois. And up at the top, the different colors, the yellows and green, is Minnesota, Wisconsin, etc. And you can see the Great Lakes. So there are two, what the colors are referring to are what we call locational marginal prices, which we are not going to go into in this class. If you want to learn a little bit more about what those are, then you should take ENEC 307 in the spring. But these are basically electricity. The colors represent different electricity prices. And so you have two systems that are right next to each other. System A, which has really low electricity prices. In fact, in the purple area, you have negative electricity prices, which means they have too much generation. There's more generation than there is demand, and they're basically saying to generators, you have to pay to sell electricity, or we'll pay you to turn your power plant off because we have too much. You have this system where there's too much electricity, it's dirt cheap, and in fact it's negative, right next to a system that is experiencing high electricity prices. So the system B, in the epicenter of that, you have electricity prices that are more than $100 per megawatt hour. So why could this possibly exist? Why could you have two systems that are right next to each other, where one has too much electricity and the other doesn't have enough? And we can tell that those are the circumstances in play because of differences in prices. Why does this exist? And it's because of transmission constraints. In theory, we would send a lot of electricity from system A to system B, but if we cannot do that because of either a lack of transmission capacity or transmission congestion, then we're just sort of stuck. And this is one of the major challenges in particular for integrating large-scale wind from the Midwest, developing those resources. When we saw that map, there's a lot of good wind resources in the Midwest, but it's really difficult to get those to the areas that could use that electricity without investing a lot of money in transmission. So the last thing here, let's talk about how the grid is organized administratively. And this, I think, from a data analytics standpoint, is useful to know because these are all the different organizations that would have different levels or details of data. And so at the very top, you have reliability organizations. These are not for-profit companies. These are non-profits that oversee everything to make sure everybody's acting in a fairly prudent way and sort of following the self-imposed rules that we all place, or the electricity utilities sort of place on each other in terms of, or on themselves in terms of making sure the system is operating reliably. Under that, you have balancing authorities. So these would include independent system operators, regional transmission organizations, and vertically integrated utilities like Duke Energy. So a vertically integrated utility would be like a publicly traded company, but independent system operators and regional transmission organizations are, again, nonprofits. So these would be people that operate deregulated electricity markets or pools of different, generators or wholesale markets, and many different utilities may be operating within the same footprint of an independent system operator or regional transmission organization. Then you have generators. Generators could be owned by utilities, or they could be part of or a company that's an independent power producer. And so I'm making the distinction here between a utility and an independent power producer, mostly to indicate that when we say utility, we generally mean somebody that has retail customers, and that would be a load-serving entity, which is the last number here. So Duke Energy would be, and so what I'm trying to say is, you can have the same company sort of be involved in multiple levels here. So Duke Energy is a vertically integrated utility, so it is sort of its own balancing authority. It's also a generator, so it's in category number 3, and it also has a retail distribution service. That's why we call it vertically integrated. It's involved in every aspect of this. The balancing authorities, I probably should have mentioned, would be involved in managing transmission systems. But here we have generators. There are classes of companies, independent power producers, that do generate electricity but do not serve directly retail customers. They just sell electricity on wholesale markets. So they sell electricity to other utilities, basically, who purchase the power and then deliver it to retail customers. So I went through a little bit about these, and so NERC, North American Electric Reliability Corporation, is a useful place to look for data on system reliability and system failures, if you wanted to look at that. They're really in charge of monitoring and enforcing compliance with standards that are developed with input from everybody about how we should operate power systems. And part of the need for this is because our power systems are interconnected physically. So problems in one area can influence other systems, and so there's an acknowledgement of that. And NERC is who is supposed to get everybody talking to everybody else to make sure things go well. So this is NERC. NERC is divided up into subsystems here. There's WEC on the west coast. We are in SERC, S-E-R-C. And then you can see there's part of NERC that involves Canada as well. Both in WEC, MRO, and NPCC, as well as Quebec. And you can see that Texas is its own island. So Texas is actually disconnected from the rest of the United States and managed. It is managed, has oversight from NERC, but it is managed as its own system. So when we think about wholesale electricity markets in the southeastern United States, we are still sort of attached to this older model of vertically integrated utilities. So like Duke Energy, they own the generation, transmission, distribution. So Duke is its own sort of balance area. They do everything, right? They haven't separated any of that out. In many other parts of the country, power systems are managed, balance areas are managed by independent system operators or regional transmission organizations. These are, again, nonprofits, but they are in place to operate wholesale electricity markets, so basically auctions for generation. They also manage transmission systems independently to make sure everybody has equal or open access to transmission systems and there's no bias there. So this is a map that shows the different RTOs and ISOs in the United States. And so where we are is still SERC, right? So that's the Southeastern Reliability Corporation. But right above us, the tan line, is PJM, right? So that PJM is Virginia, West Virginia, Maryland, Pennsylvania, New Jersey, Delaware. I don't know what else is in there before you get to New York. And then over into Ohio, Indiana, and Chicago. So this PJM is one of the largest electricity markets in the world in terms of the population of people that are served. But all these other colors are different electricity markets. So California has CalISO. The gray area in the Northwest is BPA. Texas is ERCOT. And then the blue area in the Midwest is MISO, so the Midwest Independent System Operator. So So these are the states that have competitive markets run by ISOs. So the whole Southeast is not in a competitive electricity market. That's the reason why Solar City can't come here. We still have states where there's no competition for different generators or for utilities to provide electricity to retail customers. In other states, there is competition. And so there are different ways we characterize the differences between a competitive market or the operations of an ISO versus a vertically integrated utility. And we'll talk about some of those. So, ISOs and RTOs and wholesale markets for electricity have separate markets for energy and ancillary services when we're buying or selling. So in ISOs and RTOs, different generators compete based on a bid-based cost basis for the right to sell you electricity. It's not guaranteed that every generator that signs up is going to be able to sell electricity. We only select the cheapest ones, and so there's a market for picking which generators are going to run and creating a wholesale price. There's also markets for ancillary services, so there has to be some way to convince different types of generators to provide what we call grid reliability services. So this is things that we need generators to do, but they might not do if we didn't pay them to do it. And so part of that is providing reserves, so unused capacity that can ramp up in case something bad happens, like a power plant goes out. Frequency regulation. So there are all sorts of incremental changes that need to be performed when generators are operating in terms of how much they're producing in order to make sure the grid operates at 60 hertz, as well as demand response. So this would be the opportunity for customers to actually provide an ancillary service. In this case, you're paying customers to, when the grid calls upon them or when it's economically viable for them to do this, they reduce electricity demand in order to save money, but they're also paid directly by an ISO or RTO to do this in order to promote, ultimately, system reliability. So in all these markets for electricity, but also ancillary services, the standard way that we figure out who's going to provide how much electricity and how much reserves, etc., is called economic dispatch. And so this is basically just saying we're going to find the least cost way of meeting demand for electricity, for ancillary services, for whatever. So this, on the y-axis here, you have electricity demand. And then that's what this black solid line is. And this is similar to what I showed you at the very beginning and how we're trying to fill in the area under this curve in order to meet electricity demand. And again, the goal is to do this at the lowest possible cost. And so we start with what's cheapest. And what's cheapest is renewables. Remember, I mentioned renewables we treat as demand reduction or must-take resources. So we'll pretty much always take renewables because on their variable costs are extremely low. Then we go for nuclear, and the reason we go for nuclear is because it's cheap. We also go for it because it's sort of a must-take resource as well, because it's so difficult to turn nuclear power plants off once they're online. If there's nuclear power available, we'll take it. And then where coal and natural gas are above nuclear depends on what the price of those fuels are. Historically, gas would have been up at the top here. And I guess it still is with combustion turbines. But what's really switched in the last couple of years is the positions of coal and combined cycle natural gas. Since gas has been so cheap, it's sort of switched places with coal, and that's why part of why coal plants are all retiring. So back to this final figure, it's important to understand which regulatory bodies oversee this structure. So NERC is up at the top. NERC is the reliability organization. There are government entities that oversee. I mean, I mentioned ISOs and RTOs are nonprofits. They're not publicly traded companies, but they're not the government either. And so there is government oversight of balancing authorities and generators. That's taken by FERC, the Federal Energy Regulatory Commission. And then on a more regional, state level basis, it's utility commission. So North Carolina has a utility commission that oversees Duke Energy. They work sort of collectively. I mean, the relationship between utility commissions and utilities can be pretty nebulous sometimes. But utility commissions on the state level are there to protect retail consumers in their interactions with load-serving entities, but they're also there to protect customers from decisions that are made by utilities about what generation to build, right? So the North Carolina Utility Commission basically has to determine, with some research involved, whether any decision Duke Energy makes about building something new is a prudent choice. And there's all sorts of legal consequences that come from a utility commission saying a choice by Duke Energy is prudent. That means they're guaranteed to be able to recover those costs through selling electricity or increasing prices on us. So utility commissions oversee those sorts of decisions. So this is the last slide. This was about an hour. This was a long lecture. I know there was a lot here. We were going to go over this briefly in this course, and I'll come back to a lot of these concepts in individual lectures, but for now I wanted to give you an overview of the sort of the scope of what we're going to be talking about. If you want a more detailed, less physicsy, more financial and economic view of this stuff, then you should take ENEC 307 in the spring. Where to find energy data. So I have posted an Excel file on Sakai that was given to me by Dr. Kyle Bradbury at Duke. A really nice guy, very, very sharp guy, and he actually teaches a data analytics, energy analytics course at Duke, and was helpful in helping me put this course together. He's, I'm sure, a better teacher. I think the focus of his course is a little different, but if you're really interested in machine learning type stuff, then I would actually recommend taking his class maybe next year as well. Okay, that's it. Thanks for listening.